there exists alternatives to nearest neighbor index and the nearest neighbor analysis, and today we're going to talk a bit more about one of those alternatives. So we've got point pattern analysis, or we could call it quadrat analysis. So rather than looking at the distribution of points across the entire study area, we can take that study area and divide it up into equal-sized areas, usually square cells, and look at the frequency of points in each of those squared cells. So the distribution of these frequencies within each cell can describe the arrangement of the points in the study area. So another way of looking at the distribution of points across a study area. So here's an example, a visual example of what quadrat analysis might look like, where you see our study area here has been divided up into equal-sized boxes or equal-sized cells, and our points are represented as little plus signs. So you can see within each of these equal-sized cells, there's either none or some number of points. And you can tell how many points there are in this visual example because the numbers in each cell are representative of the number of points. So imagine if we had this distribution of points, we kind of drew up this equal-sized grid, and then someone went through and jotted down the number of points within each grid box. So this is how we start quadrat analysis. So, where our nearest neighbor analysis is going to use that average spacing between points, so focusing on the closest point, quadrat analysis is going to look at the variability of the number of points from cell to cell. So going from grid box to grid box, we're going to count up all the points that are in each of them, and then look at how much that varies. Do we have a lot of boxes that are far different from the others? Or do we have most of the boxes that are relatively the same in terms of number of points per grid box or per cell? So if each cell were to contain the same number of points, there'd be no variability between them. So if you basically made a list of all the numbers of points per cell, and those were all the same, we would have no variability, and we'd say they're perfectly dispersed. So again, looking for a scenario in which we could characterize perfect dispersion. Another way of looking at it then is if there was a wide range of frequency values between the cells, we'd have a lot of variability because we'd have some cells with very, very few or no points. We'd have some cells with a lot of points or potentially all of the points. And we'd have high variability, and that would tell us that our pattern might be clustered. So again, looking at the extremes here, from perfectly clustered to perfectly dispersed. Just another way of tackling that. And then somewhere in between those two, you've got a moderate amount of variability of those frequency values, and you'd suggest something that's nearly random, as best that we could calculate from the frequency variability. So again, dispersion, clustering, and randomness are kind of our spatial indexes that we can compare to. So we can't use the absolute variability of our cell frequencies since it's going to be influenced by the density of points. We're going to have a big influence on that variability value, the absolute variability that we can calculate. So, like how we had that influence that the mean would have on a standard deviation way back when we were looking at things like that, back then we used the coefficient of variation so we could make comparisons from scenario to scenario, because we might have wildly different means, and those means are going to give different standard deviations and not allow us to compare between different areas, perhaps, where we might have different ranges of values, but we might want to compare. In the same way, absolute variability is holding us back from making those comparisons because, the frequencies are going to play a big role. So, just like where we had a coefficient of variation when we wanted to, compare, between areas, here we have an index that's known as the variance mean ratio, or the VMR. So this variance mean ratio is playing the same role that coefficient of variation played when we were dealing with means and standard deviations. And this VMR will allow us to compare between different areas. So we might have different study areas with different numbers of points and perhaps, very different amounts of absolute variability, but it allows us to make those comparisons across those differences. So our variance to mean ratio is just a standardization of our variance by our mean. So the amount of variability in those frequencies within cells to the relative mean cell frequency. So this is a very, very clean formula. You just divide your variance of cell frequencies by the mean cell frequency. And the variance of our cell frequencies and the mean cell frequency are exactly what you would think them to be. To get the mean cell frequency, you take the frequency, meaning how many points are in each cell. So if you have 16 cells, you have 16 different values, each value representing the number of points in a cell. You add those up, you divide by the number of cells, and then you have the mean cell frequency. Likewise, then, you can use those values to find the variance in the same way that we found variance before. Remember, variance is just the square of our standard deviation. So you can find the variance, you can find the mean of those frequencies, and then you divide your variance by your mean to get that variance mean ratio. So in some situations where your points might be very, very dispersed, you're going to have a value close to 0. Because remember, 0 represents perfect dispersion. And their variance is going to be very low for perfect dispersion. When there's a great deal of clustering, on the other hand, your VMR will be very high since your variance will be quite large. So if you have everything clustered up, you're going to have a lot of difference between cells because you'll have a lot in some cells, very little in other cells. Likewise, for your perfect dispersion, you're going to have low variance because you're not going to have a lot of difference cell to cell in the frequency counts. So then, in the case of a perfectly random arrangement of points, your variance and mean will probably be close to one another, and you'll get a VMR of 1. So again, just like with our nearest neighbor analysis, we've kind of set out some guidelines for what this VMR is going to represent in terms of dispersion, in terms of clustering, and in terms of randomness. So, again, we can use inferential statistics and these VMR type values. So, aside from being good in a descriptive form, we can test a distribution for randomness. We can see, is this a random distribution or is this not a random distribution? So given this, what do you think the hypotheses might be for this scenario using VMR? Well, our null hypothesis is that our VMR will equal 1. So remember, it's all about equality when it comes to a null hypothesis. Remember, 1 is the VMR value that we said is going to be approximately a random distribution of points. So if our random is represented by 1, we want to set our VMR equal to 1 because we want our null hypothesis to be the thing we try to reject. And to reject a null hypothesis of a VMR of 1, we're saying that by rejecting this, we're saying it's a distribution that is different from random. So it's a non-random distribution. So in order to say it's a non-random distribution, then we substitute in one of our alternate hypotheses. Either that our VMR is not equal to 1, meaning that we don't know whether it's going to be more clustered or more dispersed, or maybe we go with one of those two, that it's either, more dispersed, so having a VMR less than 1, or more clustered, where we have a VMR greater than 1. So those are our null and alternate hypotheses that we can set up to do some inferential statistics and some statistical tests with VMR. So then we have a nice test we can use using VMR, so we can see and try to infer whether the population from which that quadrat analysis sample was drawn is random. So to do this, we have a chi-square value, and that's going to be equal to our VMR times m minus 1. And in this case, we're going to use m as the number of cells in the study area. So notice we have m instead of n. N would be the number of points. In this case, we're using m, which is the number of cells in our study area, the number of boxes that we used to come up with this variance and this mean. So rejection of our null hypothesis in a two-tailed approach is going to say that the distribution is either more clustered or more dispersed than random. If we're going with the two-tailed approach, we don't have any expectation coming in of one way or another. We're just trying to say that it's not random. So this can result in p-values. If we're looking at that chi-square table, those can either be very high, so a very high p-value is going to suggest high dispersion, or if it's going to be clustered, it's going to be near 0. And then things in between, so in the middle, those are going to indicate a random distribution. So for that two-tailed hypothesis, either very high or very low p-values are going to reject or result in a rejection of the null hypothesis. And in our quadrat analysis we've been talking about, remember that both the size of the cells and the determination of the study area can affect the results. Just like with our nearest neighbor distances, where that had some effect that the study area played in this. Likewise, the size of our study area is going to play a role, because that's going to play a role in the number of those boxes, those cells that we're going to have, and that's part of our calculation, as well as the actual size of our cells. So how big we want those boxes to be. So in order to address part of this, then a rule of thumb is that we want our cell size to be twice the average area per point. So meaning that our average points per cell should be about 2. So if you're ever setting something up like this, you're going to want to be mindful about the size of your cells and about your study area. And try to make cell size so that when you find the average number of points that are in each cell, that you end up with something around 2. So you might need to fiddle with the sizing of your cells in order to get an average point per cell value of 2, which will tell you you're on the right track and that you aren't going to be affecting the results of your analysis by having cells that are either too big or too small.